Okay, problem 2 says that a spring is hung from a ceiling. So here's the ceiling, here's the spring, and then you attach a block of mass equals 0.350 kilograms to the free end of the spring. So this is the spring at equilibrium. Meaning that the potential energy of the spring initially is equal to 0. Then it says it's released from rest, so V initial equals 0. So the kinetic energy initial of this block is going to equal 0. And then later, the block falls. It's going to pass through its own equilibrium for simple harmonic motion before falling even a little further, overshooting that equilibrium, and then coming to rest. So the block falls, overshoots its equilibrium for simple harmonic motion, where the upward force of the spring is equal to the downward force of gravity, and then keeps going until it stops. Then stops after falling. Let's call the total distance x. X down. Let's draw that. So it's going to look like this. Now your spring is stretched out. And here's your block. Let's draw where the block was, would be right there. And then this distance that it falls, I've tried to draw over a page break there, is going to be some distance x. Okay, and it's going to lose some height as well. So it stops, so V final equals 0. So actually the kinetic energy at the end is also 0, so the kinetic energy starts at 0, ends at 0. Okay, so what is changing? We know that the potential energy of the spring increases because the spring stretches. So the spring potential energy is equal to 1/2 kx squared, where x is the new length of or the change in length of the spring. We assumed x equals 0 where it started. So we've got the kinetic energy doesn't change, but the potential energy of the spring goes up. So there's another energy here. So it's falling, right? So I guess there's gravity. So let's actually go back up, and let's not forget about gravity. Let's set the h initial equals 0. So the initial gravitational energy equals 0. And then if it falls, we're going to have h down here. So h up here was 0. H equals 0. And down here, we've got h equals negative x. So the gravitational, sorry, just adding an f to the spring potential energy, final, so gravitational final is going to be mg times h, which is going to be negative mgx. Okay, so this is good. So what's going on is the spring is gaining potential energy, but the block is losing gravitational potential energy. So that should balance out. So let's do our equation for conservation of energy, which is just that the final energy equals the initial energy. One of my favorite equations, just because it is so short. EF equals E0. So now we just expand those E's. In this case, we're going to say we've got kinetic energy plus the spring potential energy plus the gravitational potential energy, all final, equals the same thing. Kinetic plus spring potential plus gravitational potential. And then it's on the right hand side, it's all the initials. So looking upwards, scrolled off the top of the screen, but it looks like from up here, in fact, all the initial energies, as we've defined them, are 0. So let me just switch pen color here. If we use red, we'll say this is 0, this one is 0, and this one is 0. Also, the final kinetic energy is equal to 0. So back to black. If we rearrange terms here, we've got USF equals negative UG final. So plugging in our equations for that, we've got, scroll down a bit, 1/2 kx squared is equal to mgx. I want to get rid of this x squared, so I'm going to assume that x does not equal 0, so that I can divide both sides by x. If x equals 0, you can't divide by 0, so let's divide both sides by x. That will cause that x to go away and that squared to go away. And solving things out, I get k x over 2 equals mg. Now the question asks, what is the spring constant of the system? So we're actually on part A of this question. It says find k. So we solve this for k, and we get that k equals 2mg divided by x, which is 2 times 0.350 kilograms times 9.8 meters per second squared. Just going over the page break again, divided by 0.120 meters. So that should all work out. I've plugged that into my calculator. K equals 57.17 newtons per meter. Newtons per meter, I just remember, is always the units. That's our unit for spring constant. And it looks like there's 3 significant figures in this problem because of the 0.350 kilograms and the 1.120 meters. So I'm going to say that k equals 57.2 newtons per meter. And what else? Part B says find the angular frequency of the block's vibrations. So I'll just use, again, omega equals the square root of k over m. And we have all these numbers, so square root of, it's always best to use more significant figures when you're working these things out. 57.17 in SI units divided by the mass, which is the 0.350. And that's equal to, plugging into my calculator, 112.78 rad per second. So to 3 significant figures, I get omega equals 12.8 rads per second. Just want to quickly look back to make sure that this sort of makes sense. The block weighs about 0.4 0.4 kilograms. So times, where's that? Times 9.8, which is about something like 4 newtons, and falls approximately 0.1 meters. Now it actually goes a little beyond equilibrium, so equilibrium will be a little less than that. So the spring constant is equal to 4 over 0.1, just to a really approximate. It's going to be approximately 40 newtons per meter, which is, it's a little less, but it's the same order of magnitude as 57, so I think this is okay. I'm just Just doing a little bit of a sanity check to make sure my spring constant's right. So this is a little SS, which sometimes I'm too lazy to do, but there you go.